Thank you. In August 2010, 184 billion Bitcoin were accidentally created because of a bug in the code. It was called the overflow incident. And really fast, within 5 hours of this error happening, Satoshi or another developer fixed the situation and kind of hard forked the whole blockchain. And everyone just agreed with it, right? So that's why it's really important for all of you right here, right now, to kind of get involved, right? Because in the future, when Bitcoin's market capitalization is in the trillions of dollars, right? We can't wait 5 hours for a bug to be fixed, right? We need all of you to jump into the open source community and help Bitcoin, right? We need to increase the number of developers. So this talk is inspired by Shlomi Zeltzinger. He's an engineer in Israel. He has a great blog. You can go there and learn a lot more if you want to. Shlomi Zeltzinger. I'm a lead technical architect for Consensus in the Bay Area. And previously, CTO. I like to code, chess, talk about Bitcoin, smart contracts, also animal rights. Really loved what Snowden said earlier about rights are there to protect the minority from the majority. I think we can all relate to that in some instance. So now let's jump into the code, right, of creating a transaction. Now, today's transaction is going to be very specific. It's going to be it's called a P2PKH, a pay-to-public key hash transaction. So there are other types of transactions, but this is the one we're going to focus on today. And if you are interested in this, right, obviously you could go to, where was that thing? His blog, right, Shlomi's blog. But you can also go to developer.bitcoin.com, and you can just start reading right there, right? If you just start right there and find one person on GitHub, you could message me, and we can work together. So the community is really strong. So this is the type of transaction we're doing today. And we're going to be doing a raw transaction at first. So a raw transaction is one where it's not signed, right? It's not signed. It has all the information, but it's not signed. And that's the one we're going to focus on right now. All right, so jumping right into the code, this is Python 3.5. It might work on Python 3.7, I'm not sure. So we're going to focus on a common use case. Alice sent some Bitcoin to Bob, right? Alice sent 5 Bitcoin to Bob, and then Bob sends some Bitcoin to Charlie, right? So that's the situation. So let's just say Bob's sending, I think, 0.001 Bitcoin to Charlie. And actually, I'll just get the numbers right. Right, Alice sent 0.001 Bitcoin to Bob. Bob sent 0.001 Bitcoin to Charlie. He's also going to send 0.0005 Bitcoin back to himself, right, to pay the miner. Right, that's all going to be inside this one transaction. It's going to have two outputs. The first output is for Charlie, right? The first output of the transaction is for Charlie, and the next output is for the miner. Right, it goes back to himself, and he pays the miner with it. So Bob has to provide his public key and signature to be able to create a transaction to Charlie. Right, he has to provide his public key and the signature. So this is going to prove that he is actually Bob. And what's cool is I'm going to show you exactly how to do that, and it's actually not that hard. It's pretty basic. So over here, I'm going to use a few libraries. I'm going to use the Struct Library, and this is to pack the bytes into binary data, right? This is commonly used in Bitcoin applications. Also, base 58. So this is a bunch of binary to text classes that we use to take large numbers and hex code and interpret it. And it was introduced by Satoshi when he first created Bitcoin. And in plain English, base 58 is going to take our public key, right, Bob's public key, and convert it to a hash public key. That's in plain English, that's what base 58 does. Takes a public key and converts it into a hash public key. And I'll show you that code. It's basically 2 lines of code. That's it, where we kind of use base 58. And then we have hash lib, and that's to secure hashes and message digest. So basically, it's just going to let us use a bunch of different protocols, right, like ECDSA. And then over here, this is an easy-to-use implementation of the ECDSA algorithm. So this is what elliptical curve cryptography is what we use to take a private key and convert it to a public key. Right? You start off with a private key and you convert it to a public key. And that's what we're going to use ECDSA to kind of do some signing, do some verification for us. So I have a private key up here, and I know you should never share your private key, but there's basically no Bitcoin in here. There might be, but last time I checked, there is none. So go ahead, hack it, it's fine. So this is a public address. This is Bob's public address. This is his private key, and this is his private transaction ID right here. And this is Charlie's address. This is Charlie's address. So I have Bob's public address, Charlie's public address, Bob's private key. I don't have Charlie's private key because I'm not Charlie, right? I'm Bob. And so the situation again is that Bob is going to send 0.001 Bitcoin to Charlie, right? And he's going to send 0.0005 Bitcoin back to himself. So 0.001 Bitcoin is about 100,000 Satoshis, and 0.005 Bitcoin is 50,000 Satoshis. You'll see those two numbers later on. And so what is a raw transaction? So a raw transaction has all the information, right? But it doesn't contain his signature. It doesn't contain the signature that says that I am actually Bob, right? So we're going to create the raw transaction, and I think that's going to be all the time I have, but I'm going to point you to the code that refers to signing the raw transaction. So going down right here, I have a Python class. Now, we could have done this without a Python class, but whatever. It's just a very simple one, right? So the name of the class is raw transaction. And now, something in Bitcoin programming is there's something called Little Endian. And so 4 bytes in Little Endian is designated as L. And then if you want the smallest integer possible in Little Endian, it's B. So over here, there's a few parts for a raw transaction. Now, I didn't just make up these parts. If we go to the documentation, right, they're all right here from bitcoin.org/developer-reference, right? So they're all right here. So part of a raw transaction, you need the version number that you're using, the transaction in count, the length of the transaction, the length of the number of transactions that are going in, the actual transaction that's going in, the number of transactions that are going out, and then the transaction that's going out. You also need the lock time, and then there's a special hash you need at the end, which I'll talk about. So you could have as many transactions going in or out as possible. We're going to basically have one transaction going in, right? The Bitcoin that Alice sent over to Bob, and we're going to have 2 transactions going out. The Bitcoin that Bob sent to Charlie, and the Bitcoin that he's sending back to himself to pay the miner. So over here, we're just essentially, struct is to like convert it to binary. So we're specifying the version, the transactions going in, we're leaving some stuff empty. We'll fill that in later. And over here, we said 2 because we're going to have 2 transactions going out. And then over here, lock time is really interesting. You can actually say, send this transaction out in 30 days, right, if you want to. In our case, we want it to be instant, or as instant as possible, as the mining lets us be. So we're going to say 0 over here. But you could set a timestamp to do whatever you want. And then this right here, this function, it just basically reverses a string for the most part. And the reason why we have this here is to get things into Little Endian. Little Endian is to reverse the byte order. And we need to use that when we designate the proof. the proof that I am actually Bob, right? And so over here, I'm going to call the class to create an object, essentially. And over here, I'm going to update transaction in, right? And I'm going to put in a key called transaction out hash. And so I'm going to call that little Indian function, flip byte order, pass in that private transaction ID, and then convert it to binary, right? Decode to hex means converting to binary. If you encode to hex, you're converting it to hex code. And then over here, we have the transaction out index. And this is interesting right here. The transaction out index, because you might have many transactions, like transactions going out, you might have to list the index number of what you're referring to. Since I'm mainly sending this just to Charlie, there's only one, so 0, right? 0 is the first. And then over here, now this is really important. This is the signature script, right? This is how we prove that I am actually Bob. I am actually Charlie, right? Or I am actually Bob. Because what happens when someone sends Bitcoin to someone else is that they're not actually sending coins to someone else, right? They're sending a set of conditions. They're sending a set of conditions and sending a number, value. And the other person has to prove on those set of conditions, right? So the conditions are going to be like, are you actually Bob? Prove it, right? And you have to prove it. Whereas with Ethereum, it's not like that, right? It's an actual accounting system where you're kind of sending value to each other. So over here, we have base 58. That base 58, I'm calling the B58 decode check function, right? And this format, it's supposed to be very clear on the type of data that we use. Like, it uses the first few characters, and it also adds some error detection at the end. And the reason why I start off at the first character is we don't need the first character. It's something you only need when you create the public address. The first characters, it's interesting. You don't actually need it to create the transaction. So we're just going to cut that out. And then I'm going to turn it into hex code, right? Encode to hex means turn it to hex. Decode hex means convert to binary. All right, so now I have the hash public key. That's the first part that Bob needs, right? Bob needs the hash public key and then needs the signature. Those are two things that he needs to send to Charlie. And then we're going over here, and this is probably the hardest part right here. Right, now we set the script. Now over here, we see 76, A9, 14, the Bob's hash public key, that's what's going right here. And then 88 AC. So what 76 A9 is, 76 and A9, those are the opcodes from a script. It's like an output script from the previous transaction, right? It's a blockchain. So this transaction needs to refer to the previous transaction. So this transaction, in the previous transaction, there was an output script. And that output script had certain opcodes. And basically what we did was we took those opcodes, right? We took those opcodes, and let me go down over here. Oh yeah, I have all these notes over here. Right, we took those opcodes and we converted them over to hex code. And I have a URL where it does that for you. Yeah, well, right here. So if you go to bitcoin.it/wiki, hashtag opcodes, it gives you the opcode and then the hex code for it. So in our case, 76 A9, 88 AC are all converted opcodes from the output script of the transaction that Alice sent to Bob. And then over here, where was it? Right here. We have 14. 14, let me see, right here. Yeah, 14 is in hex code. It's actually 20 in bytes. And basically what it is, we're converting the number of bytes of the hash in the output scripts into hex. So we're just converting the number of bytes that the output hash like physically is into bytes. Into hex. In bytes, it's 20 bytes, and in hex, it's 14. So over here, we put 14 right here. And then this is our script. This right here are the conditions that Bob is setting that Charlie must prove. So Charlie must prove, that's for the next transaction. These are the conditions that Alice has set for Bob to prove that Bob is actually Bob, right? That's why we provide the Bob's hash public key and then these conditions right here. And these conditions are basically converted from the output script from the previous transaction. And you can find the output script from blockchain.info. You just put the transaction in, you click on the previous transaction, you scroll down, and the output script is right there. And you just convert it using a chart. That's it. And what's interesting is we have the script bytes, and we have to get the length of the script, the output script. So this is how we get the length of the output script, the amount of bytes it takes. Again, this B stands for the lowest possible integer in Little Endian. So we're just getting the length of this script right here. That's what we're doing. And then we have the sequence, and this is basically default. It's this 0xFFFFF, and we convert it into binary. So this is always the same for every Bitcoin transaction right here. We just have to include it in the raw transaction. Now, that was the first transaction. That was the first thing. Now, we have to go, that was the first transaction coming in. Now, there's two transactions going out. And the transactions going out are actually super, super similar to the transactions going in. So over here, I'm designating transaction out 1 value. And 100,000 Satoshis is how much Bitcoin? It's 0.001 Bitcoin, right? So you always designate Satoshis. And always, if you're gonna send out a transaction like this, which you might do if you're creating a wallet, or maybe if you're working on a Bitcoin ATM, or you're working on a multi-sig, I don't know, like you might be doing this. So you gotta make sure that this number's correct before you send the transaction out. And Q is how we designate 8 bytes in Little Endian. Q is 8 bytes in Little Endian. And there's a site called BTC Satoshi that you could just put in how many Satoshis, see the dollar amount, and then there's this chart over here that just tells you how much Bitcoin is how much Satoshis. Just does a conversion for you, which is nice. So after we get the value, then we get the hash public key, right? We create the hashed public key using the base 58 package, right? And then we make sure that Charlie has to prove that he is Charlie, right here. That's what this is doing. These are the conditions that were set in the output script, converted, and then we make sure Charlie is actually Charlie by having him prove that he can fulfill these conditions over here, right? And then we get the length of this script over here, and we put that in the raw transaction. So it's transactions going in are very similar to transactions going out, extremely similar. And then over here, we have the second transaction. The first transaction going out is to Charlie. The second one is the Bitcoin coming back, the 0.005 Bitcoin coming back, 3 zeros, that he's going to pay to the miner, that he's paying to the miner. And then here, this is us constructing the raw transaction. This is the raw transaction. And all we're doing is kind of adding everything in a certain order. And how that order is determined is based on this binary map, right, that Satoshi made, this binary map. And this is a horrible picture. I had a better one, but I couldn't find it. Because this doesn't have any labels on it. There are pictures of binary maps with labels on it. This includes the Coinbase also. When you have a transaction with a Coinbase, it's more for mining, right? It's more for miners, and we're not mining right now. So the reason why it's in the order that it is right here is because of that binary map that Satoshi made. And then at the end over here, this is really important for the raw transaction, but we're going to drop this last thing on line 174 for the real transaction. For the actual transaction, we're going to drop it, but for now, we have to kind of put it there for the raw transaction. It's important. And then over here, this is the signing stuff, right? Because all of this remember, a raw transaction isn't signed. It's not something you can actually send, right? You need to sign it. So over here, this is the signing part. And I don't have time to go over it right now because I'm eating up time. But over here, this is my LinkedIn and this is my email. If you want the code, just shoot me an email or a LinkedIn message. I'll send it over to you. And if you have questions about it, I can answer it. Again, it's super important for you guys. You guys are here for a reason. You guys want to be Bitcoin developers, right? Something inside of you, right, is like, I want to be a Bitcoin developer. And we kind of need you. The community needs you to make it stronger, right? For the future of the world, we need you. So please go to developer.bitcoin.it and also check out Shlomi's blog, right? Shlomi's blog, and keep going. Thanks, guys.